Welcome back. Last time we talked about pH, and today is what right now we're gonna talk about pOH, which is related to pH. So pH is the concentration of protons in solution, and pOH is simply the concentration of hydroxide ions in solution. And like there was a way to calculate pH, there's a way to calculate pOH. But what we're really interested here is the relationship between pH on one hand and pOH on the other hand. So the relationship between proton concentration and hydroxide ion concentration. Just to recap why this is important. This is important because cells of organisms and ecosystems, for that matter, do not tolerate changes in pH and consequently pOH well. They are very, very damaging, and so that'll lead us next time to a discussion of buffers, which are ways in which we can maintain steady, stable states in terms of pH and pOH. So we'll talk about some mechanisms of homeostasis. So to introduce this idea, I want to go back to water, and what I'm going to talk about here, which I mentioned briefly last time, was this idea of water dissociating. So you see here is a water molecule. So we've got the red oxygen atom there and the two white hydrogen atoms. So we've got H2O, as you know. Now, at a very low frequency, what will happen is that in pure water, the water molecule will break, it'll split apart. And so what happens there is we get left with a proton, a H+, because the electron from one of the hydrogens is pulled by the oxygen, which stays with one of the hydrogens, and that produces a hydroxide ion. And so we have an OH-, which has the electron from the other hydrogen atom, and a proton. So if you take one water molecule, you can get one proton and one hydroxide ion. Now this happens very, very infrequently in water. In fact, it happens so that in a liter of water, you would have 10 to the minus 7 moles of protons. That's a tiny number. So if you've got 10 to the minus 7 moles of protons, that gives you the pH of 7. We said last time that it's 10 to the minus pH. If the pH is 7, that's 10 to the minus 7. Now, the interesting thing is that you must always get one hydroxide for every single proton. So that means that in pure water, there's an equal number of protons and an equal number of hydroxide ions. And so if you look at the sum of both of those, and the way that we look at the sum of those is we multiply the proton concentration by the hydroxide concentration, which you can see here in this next slide. So we've got on the left the concentration of hydroxide ions multiplied by the concentration of protons. And in pure water, remember this is pure water, so we'll start off with that as an example. If the proton concentration must be 10 to the minus 7 in pure water, and for every single proton you have a hydroxide ion, that means that in pure water the hydroxide ion concentration must be 10 to the minus 7. So 10 to the minus 7 multiplied by 10 to the minus 7, if you don't believe me, do it on your calculator, is 10 to the minus 14 molar. So when you multiply logs, you just simply add them together. So minus 7 plus minus 7 is 10 to the minus 14 here. So the cool thing about this is that it doesn't matter what the pH of the solution is. If you take the hydroxide ion concentration and multiply it by the proton concentration, you always get 10 to the minus 14 molar. Always. So whatever this number is for hydroxide ion concentration, whatever this number is, they will always end up being 10 to the minus 14 molar when you multiply those together. So when you take the product of those two things. So it doesn't matter what OH- is, doesn't matter what H+ is, they both end up multiplying to give you 10 to the minus 14 molar. So what is neat is that you can rearrange this equation to solve for the hydroxide ion concentration or for the proton concentration. As long as you've got two of these variables, as long as you've got OH- and 10 to the minus 14, and you know that 10 to the minus 14 is always going to be the way. So as long as you've got OH- or H+, you can rearrange this equation to solve for the thing you're missing. So you should be able to do this algebraically. Now, if the logs and all that kind of thing confuse you, think about it like this. It is A times B equals 10 to the minus 14 molar. And so you should be able to rearrange A times B equals 10 to the minus 14 to solve for A or B. And then if we substitute in a value for A or B, you can rearrange the equation to solve for the thing that you're missing. If I give you A, you should be able to give me B. If I give you OH minus, you should be able to give me proton concentration. So I'll put a little kind of what I call a live scribe, which is where I can work out things on a piece of paper and record that, and I'll post that in Canvas, and you can take a look at that to see what exactly that looks like, how to solve that and rearrange it. But you should be able to do that from high school algebra. Okay, so that's the take-home message from this part, really, is that proton concentration multiplied by hydroxide ion concentration always equals 10 to the minus 14 molar. Now, if you're already struggling with, oh, what's a molar? You've got to go back and look at that video that we talked about concentration in. Okay, so we'll finish up. Just one quick question for you to look at. See how I get on with this. If you can do this, you're probably getting this stuff pretty well by now. Here we go. Okay, that's it. Look out for the LiveScribe podcast or pencast of how you rearrange that equation to solve these problems. And I will see you next time we're talking about buffers.